All right, class, let's try another good one. This one says that we have two waves simultaneously present on a long string, and they are given by this function. Now, this problem is really very interesting because this first equation is a wave, and because of the minus sign, is traveling in the positive direction. But it has a phase shift. Now, the second wave is of same amplitude. Oh, oops, I forgot my sign there. Let's try that again. Sine of kx minus omega t plus phi. So it's a sine wave with a certain wavelength and frequency traveling in the positive direction and is shifted by a phase. The second wave is just like the first, has the same amplitude, it has the same wavelength, has the same frequency, but the difference is it's traveling to the left, and of course the phi means that the two are out of phase. Now, the reason this is kind of interesting is because in class and in the book, we did the case where phi is equal to 0. We called this a standing wave. Maybe I won't go through all the math again, but if phi came out to be 0, we got this. We got 2a, then we got the sine of kx, then we got the cosine of omega t. And a drawing of this would show that if you plotted it, say, at time equals to 0, and so if this is your grid line, you would have a sine function that would go up and then down and then up and then down and up and then down, and same thing in the other direction. And then as time increased, you would get something that looks like this. And so the positions of the 0 doesn't move. That's why we called it a node. A little bit later, the time would be such that the cosine function would become a little bit negative. So you might get something that looked like this. And then ultimately, this would become a negative one, where then you would get something that looked like this. So I hope all these drawings didn't confuse you. It doesn't do all of these at one moment in time, but these are different snapshots, if you will, at different moments in time. But there's these magical points that we kept calling nodes in our standing wave pattern. And these magical points, are always at 0. And so this thing looks more like it's breathing. These get, of course, this one's up, this one's down, and they just keep kind of toggling like that. But there's no movement, there's no traveling. And that kind of makes sense because what we have is one wave going to the right and another wave going to the left. This is an interesting question because we didn't do anything like this, but that's why this is an interesting question, because you're going to see that if there's a phase between them, it's kind of irrelevant. All that really does is where you pick your origin to be. And so if we, were to pick our origin here or here, then we would just have a phase between them. But we would still have a wave going to the left and going to the right. Let me get some colored pens here because I that's really what this problem is all about, to get you to see that there's nothing really new and nothing really interesting, and so we didn't do it in our discussion. And this problem is to show you that throwing in a phase is just where you put the origin, and so that's like saying there's a difference between a sine and a cosine. Sine and cosine, they're the same silly thing. It's just where do you put the origin, and so it just really doesn't matter. And so we don't really pay much physical attention to it. I realize mathematically it's different, but that's for mathematicians to think about and worry about. It's really just where we're putting our origin. Okay, so let's go through this. A says, do the two traveling waves add to give a standing wave? Explain. And yes, let's do exactly the same thing. And what we did was this. We used the trig identity that if you have the sine of angle A and you add it to the sine of angle B, And again, maybe you need to go back to look where we did the standing wave where we had phi equals to 0. We said if you do that, you get 2, and you get the cosine of the difference divided by 2 multiplied by the sine of them added, so the average, okay? And I'm going to use that same identity here, okay? So this right here, this whole thing is going to be A, and this whole thing is going to be B. They have the same amplitude, so when you add them together, we can factor out an A. The trig identity shows us that there'd be a factor of 2. Then we would subtract the 2. So we would go kx minus a kx, that's gone, minus omega t, so that'd be minus 2 omega t's, and then plus a phi, all divided by 2. Okay, I'll work on that one in just a second. This one here would be then the sine, and you would add them. So kx plus kx makes 2 kx's, minus omega t and plus omega t make 0. Then if you add this, you go plus phi, and then all that divided by 2. Okay. Now, when we simplified it, we didn't have a phi. So we did something like this. We wrote the sine first. I don't know if that really matters. But if I write the sine first, I get sine, and this becomes kx, and I get phi over 2. And we also, and again, I don't know if it's really necessary this time, but we said the cosine was an odd function. I'm sorry, an even function. And so putting an extra negative in everything didn't really affect it. So without the phi, we just had the negative omega t, and then we just wrote omega t. And I guess I'm going to follow that pattern. I'm going to divide by the 2 and the omega t, but I'm also going to multiply by a negative, and that doesn't change anything. So I'm going to omega t, and that's going to go minus phi over 2. And so I want you to kind of look back here and say, okay, well, that kind of looks the same. And yeah, sure enough, it looks the same. Okay, there is no real significance here. In other words, if you went to plot this, what would it look like? Again, other than this little factor here, you would have something that you might say would look like this. Let me just pick an origin. Actually, maybe I shouldn't pick an origin, and maybe that just makes it kind of harder to think about it first. You know, I would just say that without picking where the origin is, and I just pick some moment in time, all right, so some moment in time, so that would be a number, and there's the 2a, but then I would get my sine function. Now, granted, the origin would not be here. In fact, maybe it's best to write this as a minus negative phi over 2, because we know from our algebra class that if you have f of x, then f of x minus a is that same function just shifted by a. So this is saying I would have a sine function, and sine function normally would be, I'll put the origin right there for a normal sine function. And so this is saying you would shift shift the function by a negative phi over 2. So, see if I'm saying this right. If I were to shift the function that way, that essentially would make the origin, let me just put the origin here then. So all this is saying is that I would still have a standing wave pattern. I would still have this same variation, the same variation right there with x. It would just be shifted. And, of course, also shifted in time. That is, if this was a drawing at t equals to 0, then you would have cosine of some number, and it would be less than 1, so this wouldn't be its full maximum. And so as the time got bigger, at some point the time would be equal to that, and then you would get cosine of 0, and you get 1. So what would happen is this thing would eventually get bigger, and then would look like this. But it still would reach its maximum of 2a when the cosine function is 1. It's just not doing it at time equals to 0. It's doing it at some later moment in time. And also it's not reaching a 0. There's not a node at the origin. It's been shifted from the origin. But other than that, it looks exactly the same here. And so now you can see why, and this was the whole point of this problem, that if you study it with a phase shift, you really don't get anything new. And so, yes, you get a standing wave pattern. So I think that was the question. Let me go and write A. So what's A? 16 says, do the two traveling waves, yes. Explain. And I guess I'd say, hey, it's the same effect, it's the same pattern. It's just that the origin is shifting. Both the origin of space and the origin of time. In fact, I'm not sure really how to put those in words. Let's see what the author says here. It says the result is, and let's see, did we get the same thing? Yeah. And he just says the oscillations of sine kx plus phi factor means that the wave shows alternative nodes and antinodes and therefore is a standing wave. Yeah, so it's a standing wave. It's the same mathematical pattern, just shifted. So, yeah, I don't know how to answer that. It's just, it's one of these things that is a math answer. It's like, well, look at the equation. It's the same silly thing. This is the same thing with a shift. That's why we learned that back in our algebra class. Okay, then what was part B? Something about it doesn't have nodes, or let's see, part B. Is it still true that the nodes are a half wavelength? Yeah. You can see the variation comes from here. All this did was shift it. I suppose you could say something like this, that's kx plus phi over 2 would give you your nodes when the argument of the trig function is either 0 or pi or 2 pi or 3 pi. Maybe the way to write it is an integer multiples of pi, where n is 0, 1, 2, 3. That should be plus or minus. Plus or minus, plus or minus, plus or minus, pi, 2 pi, 3 pi. And so if you bring this to the other side and go, well, kx then, and so we're looking for the shift in x when it goes from one node to another node, it would be n pi and then minus phi over 2. So if you wanted to know, when it went from 1, 0 to another, you would say, well, at n plus 1 pi minus pi over 2. and then the one previous to it, n pi minus pi over 2. So that's the difference between 1, 0, and the next. So that's from one node to another node. You would have this k times this delta x. How far did it go? But you can see then the phase is irrelevant. This minus phi over 2 and this plus phi over 2, they cancel off. And in fact, even the n pi's cancel off, and you're stuck with this pi. And so this k delta x is still pi. Or solve for delta x, you would have pi over k, and remember pi is 2 pi over lambda. The pi's cancel off, and you get lambda over 2. And so there's your mathematical proof that the nodes are a half wavelength apart. And when we did that in class, we just, of course, had kx. We didn't have this extra phi over 2. We didn't have this shift. But again, as we did in part A, that's really kind of irrelevant. We proved in part A that everything would look exactly the same. It just shifted. So if they were half a wavelength apart before, they're half a wavelength apart now. And that, like I said, would be kind of the mathematical proof for that. Okay, and C, are the nodes different in any way from the way they would have been when phi equals to 0? And again, no, but with a shift. So I guess the answer is, yeah, slightly they are shifted. And as we mentioned over here in the mathematics, we could write this as a sine of kx, and instead of writing it as plus phi over 2, we could write this as sine kx minus a negative phi over 2. Because that would fit our function of something like this, sine of kx. Now we have sine of kx minus something. And that fits our pattern of f of x, and then f of x minus a. And that just means it gets shifted. So we could get shifted by a negative pi over 2 is, I guess, the way I would answer. And so maybe I should put shifted by negative phi over 2. Actually, I should be careful. That's actually the phase shift, but on the x-axis, I guess I would be dividing by k. So let me say it this way, that the x would, I guess the kx, well, how am I saying this? So I guess the k times the x shifted would be the negative pi over 2. So the amount of x of the shift would be a minus phi over 2k. And so how far on the x-axis might be a better way to answer this. So how far did it shift on the x-axis? So anyways, this was a good a math review here. In fact, maybe I should just flip over here to the answer. Oh, good. They put phi over 2, but they didn't put a minus. Oh, they say to the left. All right. So to the left. That's what the negative is. So to the left, phi over 2k. All right. Hope that helps.